And in fact, the attention mechanism is a so good idea that they came up with an architecture that is completely based on attention, which is the transformer. So, before introducing the transformer, let's look at what we have at this point. We have a sequence-to-sequence model that is able to address tasks where we have sequencing input, sequencing output, but we have full flexibility. We don't have any constraint on the number of elements. To make it even better, we added the attention mechanism, which allows the decoder to look back at the input and code sequence to extract the relevant information on demand. And we saw that this is working really well. But there is one detail that we still have RNNs in a sequence-to-sequence model. If you remember, the sequence-to-sequence is basically this encoder and decoder, and we have an RNN, which can be the TANH, the LSTM, or the GRU, in the encoder, and we have another RNN in the decoder. So we are still using RNN. And unfortunately, the RNNs, they have two problems that we would like to overcome. So the first problem is that they are not easy to parallelize. And we will see more in detail about this. And the second problem is, even if we use the very complex implementation, like the LSTM implementation that we saw at the end of the first presentation, they still struggle to capture very long-term dependencies. Like if I have many, many words, because maybe I'm working with text, if I have, I don't know, 300 words, given the nature of the RNN, they will still struggle to capture these long-term dependencies. And now I will show more details about these two problems. So the first thing is they are not easy to parallelize, and this comes from the architecture itself. Like if you remember, the RNN is basically running some functions again and again at every time step. And when running this function, it needs to look at the previous internal state. So if you see it here, let's say that we want to compute H4. In order to compute H4, I need to know H3. So, and in order to compute H3, I need to know H2, and so on. So you see that we have a order here on the computation. I have to start with the first H0. Only when I am done with this computation, I can start with H1 and do H1, and only when I am done, I can go to H2, and so on. So you see there is a temporal order here. And this is something that we don't like, because as it has already been mentioned in the previous days, GPUs and TPUs, they are really, really good in running things in parallel. And this is something that we cannot run in parallel because of this chain of computation. What we would like here, for example, is to run all these H0, H1, H2, H3, and H4 all in parallel at the same time. That would be very efficient for our training. Instead here, it's not efficient because even if I have the capacity on my GPU to run many things in parallel, I'm not using that because I need to follow this order. So this is something that we would like to remove. Second problem I mentioned is this long-term dependency. So you may remember this slide. We used that to introduce the exploding gradient and the vanishing gradient. And we said that with the LSTM, we strongly mitigate the vanishing gradient problem. But still, if you look at the nature of RNN, which also includes LSTM and GRUs, the only way for the information to flow is to go through all these internal states. And that means that, again, if this sequence is maybe 200, 300 elements, and I need to capture these very long dependencies, still the information has to flow for many, many, many steps. And even if in the LSTM, for example, we have the memory cell, this can be a problem because we are talking about very long sequences. And the information has to flow over all these elements in the sequence. So this is another problem that we would like to solve or at least mitigate. And this will, okay, and before introducing the transformer, so let's see this in light of the sequence-to-sequence model plus attention. So we said that the RNN, we would like to find a replacement to deal with these two problems that I mentioned. But if we look at the sequence-to-sequence architecture, at the full architecture, there are also things that we want to keep. So, okay, we want to remove the RNN part, as you see here. But we want to keep some stuff. We want to keep the encoder-decoder architecture because we saw that it is a very efficient way to deal with these problems where the input sequence is different from the output sequence. So we want to keep this encoder-decoder structure. We want to keep the attention mechanism. We saw how the attention mechanism is definitely improving the flow of information in this model. And we want to keep the autoregressive nature of the decoder because we saw how this is a very clever way to generate output that is also consistent because the decoder always knows what was produced before. So we want to keep these points in mind when creating this new architecture that we will call transformer.